Hi everybody, welcome to Multirate Signal Processing. Today about effects in the Z-domain. So we saw the Z-transform is a more general transform than the Fourier transform, and we will use it to obtain perfect reconstruction in filter banks and wavelets. Hence we will now look at the effects of sampling and some more tools in the Z-domain. So since we usually deal with causal systems in practice, we use the one-sided Z-transform, defined as capital X of Z is defined as the sum from 0 going to infinity over x of n times z to the minus n. So basically this takes our sequence of samples x of n and turns it into a polynomial capital X of Z, right? Notice that there's no n anymore, just a complex variable z, which is the polynomial variable. So first observe that we get our usual frequency response, the discrete time Fourier transform, if we evaluate the Z-transform along the unit circle on the Z-domain. So if we just take z as on the unit circle, here we have e to the j omega. So omega is our angle going from 0 all the way to 2 pi, and this basically samples or covers the unit circle on the complex Z-domain. And if you plug in this substitution into this formula, we see that it is basically the discrete time Fourier transform for causal signals, right? So it's basically identical, except that here in the argument now we have e to the j omega instead of just omega. But that's the just a notational difference. So basically we see that the Z-transform is a generalization of the discrete time Fourier transform in this way, because Z can also be on other places on the complex Z-domain. So what is now the effect of multiplying our signal with a unit pulse train in the Z-domain? So remember we had this multiplication with a unit pulse train as the first step of sampling, right? We take our signal and we want to downsample it, for instance, then we multiply the samples that we want to keep with a 1 and everything in between with 0. To see this, we simply apply the Z-transform to and use our sum formulation for the delta impulse train. So here we can see it. Here, instead of just having x, we have x times our unit pulse train, where we just keep the samples on the new sampling grid and zeros in between, and then we have it in this Z-transform, where we have the sum and the z to the minus n. So this is now the Z-transform of our downsampled signal, including the zeros. So this doesn't tell us too much yet, but it will become more obvious if we replace this delta, this unit pulse train, by this sum formulation, which I took from the lecture Advanced Digital Signal Processing, slides number 6. So here you can see the representation of the unit pulse train as the sum of complex exponentials. So it's not obvious to see in this sum formulation, but you can imagine it as consisting of the fundamental frequency and its harmonics from this unit pulse train. So here with k equals 1 we have the fundamental frequency, then the higher k's give us the harmonics, and k equals 0 gives us the DC offset. So it's basically the inverse Fourier transform of this spectral structure. Yeah, so when you want to know how it's derived, go to the slide set, and there it's derived. So then we know that it's correct. So then we can just take this formulation using the sum of exponentials and plug it into the Z-transform formulation here. And we get a double sum, right? Here we have the sum from the unit pulse train, and this sum comes from the Z-transform. And here we can see we have our complex exponentials, here the z from the Ztransform. And we see that this inner part has a lot of similarity to the Ztransform of x, except that we have this factor here in front of it, in front of the z, right? So this is basically the the Ztransform of x. So here we can see it in the next row, x, capital X, the Ztransform of lowercase x. And instead of just z, we have this e to the minus j 2 pi over n times k times z. Right? This came from here. So here basically this inner part is now becoming this Ztransform. And then this outer sum remains from our sum of the unit pulse train. So now we have n summons starting from k equals 0 up to n minus 1, capital N minus 1, and each of those summons represents a Z-transform, but a modified Z-transform with this e to the minus j 2 pi over n times k. Right. And this actually makes sense when you think about the connection to the discrete time Fourier transform, right? Remember, we can replace z by e to the j 2 pi over n times k times z here in this expression here, and then basically this is the result, right? So we basically have those modified Z-transforms. Yeah, so this is indeed similar to what we get from the discrete time Fourier transform. When we see that z is e to the j omega, right? That's the connection to the DTFT. And then basically those exponents, the omega and this exponent here, add up. And then we have frequency shifted versions. Right? Omega was not just our angle, but it was also our normalized frequency. And then we have our normalized frequency omega plus minus 2 pi over n times k. Right? And this is basically the shifted frequency components. Yeah, so we get a sum with alias components, just that we now don't have frequency shift or aliasing terms by multiplication of but a multiplication of the exponential functions to z. Here we effectively shift the phase or use rotation of the complex number z using this complex exponential. So typo exponential. This also makes sense since the frequency information is contained in the phase or the angle of z, which we see if we replace z by e to the j omega, as I just mentioned. So in the DTFT, omega is also the normalized frequency. So the next effect is the removal or reinsertion of the zeros from or into the signal. Let's again use our definition, y of lowercase m. M is the index at the lower sampling rate, is xd, which contains still the zeros, but this xd is now addressed only at the samples which are unequal to 0. So that meaning the ym is the signal without the zeros. Then the Z-transform becomes this, so y of z, here we have the Z-transform of it, and here we can plug in the information or the formulation for the downsampled xd. And now we can replace the sum index m here, the lower sampling rate by the higher sampling rate, n equals mn, capital N, and observing that the sequence xd contains the zeros with xd of n equals 0 for n unequal m, capital N. And this results in this expression here using the index substitution n equals mn. So here we have it. We have this expression here, right? And now we use the index substitution, n equals n mn. And here we can see instead of m, we have n divided by n, right, from the index substitution. Here we don't really need to change anything because mn turns into lowercase n. And this then gives us the Z-transform. Here we have the Z-transform of xt, but now with the argument z to the power of 1 over n. Right. So we see that we get the 1 over n in the exponent of z, or in short, we get y of z equals xt of z to the power of 1 over n. So the exponent 1 over n of z now corresponds to the stretching of our frequency scale in the Fourier spectrum. So this is exactly this factor of n that we had in the DTFT. Yeah, another useful tool was modulation, which we already saw. This is the multiplication of our signal with a periodic function, for instance an exponential function. It can be written as this. So we have our signal x of n, and then we multiply it with some periodic function, for instance this exponential. So remember, usually we have sine or cosine, but they just consist of two of those complex exponentials. So this is a very generic formulation. So omega m is then our modulation frequency, and m denotes the modulation here in this subscript. Yeah, observe that the modulation function here has a periodicity of 2 pi divided by omega n. Its Z-transform hence becomes this. So here we have our signal, the modulated signal, and we apply the Z-transform to it, the sum here. And then we can see, since we have this constant to the power of n, we just can take the product of the two and have the exponent n, or the exponent minus n. And then we have the Fourier transform, but with a modified z. Here we can see it's modified by multiplying it with e to the j omega m. Right. So here again we have this rotation. Here this e to the j omega m means we have a rotation of z by the angle omega m by this exponential factor. And again, this corresponds to a frequency shift by a normalized frequency omega m in the DTFT domain. Yeah, then we have time reversal. That's another important tool. It's the reversal of the ordering of a finite length signal or our sequence with length L, meaning xn is non-zero only for n equals 0 to n minus 1. And then the time reversed version simply starts at the end and goes down to 0, right, as you can see here. And if we then apply the Z-transform, we expect it to be quite similar basically, because it's just time reversed. So let's check. Here is the Z-transform of this time reversed version. Everything is the same except here for the index, which is flipped. We can now reverse the order of the summation, of course without affecting the result, by starting at the highest index and going to the lowest, replacing the index lowercase n by the expression n minus 1 minus n prime. That's our index substitution. So here we just reverse the ordering by doing this index substitution. And this is what we get. Now instead of having n, we have n prime, which comes from here. Still goes to infinity. Actually, it stops when the signal becomes 0. So the infinity here is just convenience because the signal is finite. And then we have the index substitution that turns the argument from L minus 1 minus n into an n prime. So this is what we need to get the usual Z-transform of x. And then we have a modified exponent of our z. So instead of having z to the minus n, we now have z to the minus L minus 1 minus n. And this is basically a constant, the first part. The z minus L minus 1 is not dependent on n prime, and hence we can factor it out of this sum, right? So it can go in front of the sum. So that's what we see here in the next row. You have z to the minus L minus 1 in front of the sum, and then the sum here is simply the Z-transform of x, but with a minus sign here. So we have z to the minus 1 instead of z, right? Remember here, usually we just have minus n. Here we have another minus here, so we have a z to the minus 1. So that means the reversed the Z-transform of the reverse sequence has z to the minus 1 as the argument of the Z-transform. And then it has this constant factor which basically comes from this delay from making the flipping causal. Yeah. So remember, this was the Z-transform. So in this way we have the connection between the forward Z-transform and the Z-transform of our signal and the Z-transform of our flipped signal. So what we obtain is the inverse of the z in the Z-transform, which signifies the time reversal, and this factor of z to the minus L minus 1, which is simply a delay of L minus 1 samples. Important here is the inverse of z. Yeah, so what difference does this make in our Fourier spectrum? Replacing z by e to the j omega, we obtain x of minus omega instead of x of omega, right? Taking basically this principle back to the dt of t. For real valued signals, this only makes a difference for the phases of our frequency responses, because they are then sign flipped because of the spectral symmetries for real valued signals. But the magnitudes are identical because of those symmetries. But this can still be of importance, for instance, in filter banks with aliasing cancellation. Here the different signs also change the sign of alias components, and that can make the difference between alias components cancelling between different bands or adding up. So that's really important for reconstruction and aliasing cancellation. For complex valued signals, the negative and positive frequencies can be completely different, and hence time reversal would make a bigger difference. Yeah, and that's it for this set of slides. Thank you for your attention, and then see you next time.